Why did the share price of Chinese rare earth mining companies drop because of one sentence spoken by a Tesla engineer on a stage in Texas? March 1st, 2023. Colin Campbell, Tesla's vice president of powertrain engineering, stood up at Investor Day and said the company had designed its next drive unit, a permanent magnet motor, to use no rare earth materials at all. Then he put the numbers on a slide. The motor in a Model Y uses 3 separate rare earth elements, roughly 500 grams of the first one, about 10 grams each of the other 2. The next generation motor, according to that slide, would use 0 grams of all 3. Shares in Chinese rare earth miners fell after those comments. One sentence, one slide, and a mining sector moved. That was 3 years ago. As of early 2026, no rare earth-free Tesla drive unit has appeared in any public filing, production disclosure, or investor material. The motor Tesla just put in its fastest Model Y still uses magnets that depend on China. This is the story of the hardest engineering problem in the electric car industry, and why the company most determined to solve it has not solved it yet. And here is the strange part. Tesla is named after the man who invented a motor that never needed a magnet in the first place. Nikola Tesla's AC induction motor generates its own magnetic field from electricity. No neodymium, no mining, no China. Tesla built its first cars with exactly that kind of motor, then deliberately walked away from it. Understanding why they walked away is the whole story. Before we get into it, make sure to subscribe to the channel so you can watch videos like this before anyone else. To understand why 2023 mattered, you have to go back to a decision Tesla made in 2017 that almost nobody outside the industry noticed at the time. It is the decision that created the problem the company has been trying to engineer its way out of ever since. Start with the name. Nikola Tesla's great contribution to electricity was the alternating current induction motor. In an induction motor, the rotating part carries no magnets at all. The stator creates a rotating magnetic field. That field induces a current in the rotor, and the induced current creates a second magnetic field that chases the first one around. The rotor makes its own magnetism out of electricity, on demand. That design has one enormous advantage that mattered very little in the 20th century, and matters enormously now. It needs no rare earth elements. None. The original Tesla Roadster used an induction motor. So did the Model S. For the first decade of the company's existence, Tesla built cars around the technology the company was named after, and it worked. Then came the Model 3 in 2017, and Tesla changed course. The Model 3 introduced a permanent magnet motor. Instead of inducing magnetism in the rotor carries fixed magnets made from neodymium iron boron, and the stator's rotating field pulls directly on them. The reason is efficiency, and it is not a small difference. An induction motor spends part of its energy budget continuously generating the rotor's magnetic field. Every second the car is moving, some of the electricity from the battery goes into making magnetism rather than making motion. A permanent magnet motor gets that magnetism for free, because the magnets are already magnetic. That energy goes to the wheels instead. More torque at low speed. Better efficiency at the speeds people actually drive. More range from the same battery. For a company trying to build an affordable long-range car, the choice made itself. Permanent magnets won, and the entire industry made the same call. Almost every electric vehicle on the road today uses a permanent magnet synchronous motor. But here is what that choice cost, and it is a bill that came due much later. Neodymium magnets require rare earth elements, and the global supply of those elements is heavily concentrated in China, both in mining and, more importantly, in the processing. A car company can find deposits in other countries. Turning the ore into magnet-grade material is a different problem, and that is the part China dominates. So a decision made purely on efficiency in 2017 quietly handed a strategic dependency to every automaker that copied it. Nobody was thinking about supply chain leverage in 2017. They were thinking about range, which means when Tesla announced in 2023 that it wanted a permanent magnet motor with 0 rare earths, it was not chasing a performance target. It was trying to undo a trade it made 6 years earlier, without giving back any of the efficiency it bought. That is the actual engineering brief, and it is far harder than it sounds. The single sentence this whole video hangs on is this: a permanent magnet motor is only as good as the magnet, and the best magnets on Earth are made from a material one country controls. Hold on to that, because every decision that follows comes back to it. And the problem is measurable, not vague. Take the strongest ferrite magnet grade generally available, the obvious rare earth-free alternative, and compare it against the neodymium grade typically assumed to be in a Model 3 motor. The ferrite magnet has roughly 1/9 of the maximum energy product. Its resistance to demagnetization is more than 3 times lower. 1/9. That is the gap any engineer trying to delete rare earths has to close, and it cannot be closed with a better factory or a smarter supplier deal. It has to be closed with physics. So when you hear that Tesla is working on a motor without rare earths, what you are actually hearing is a company trying to build a magnet 9 times weaker into a motor that performs the same. Everything else in this video is a consequence of that number. So how do you get a weak magnet to do a strong magnet's job? There are only a handful of levers, and Tesla has been pulling all of them. The first lever is geometry. If the magnet is weaker, you need more surface area where the magnetic field does its work. In a motor, that is the air gap, the narrow space between the spinning rotor and the stationary stator, and it is where almost all of the magnetic energy is concentrated. Independent motor engineers modeling rare earth-free designs have converged on the same answer. To use weaker magnets without making the motor bigger, you have to expand the air gap area, which usually means changing the shape of the motor itself rather than just its contents. The second lever is speed. Power is torque multiplied by rotational speed. If weaker magnets cost you torque, you can recover the power by spinning faster. And this is where Tesla's most visible piece of motor engineering comes in. In 2021, the Model S Plaid launched with what Tesla says was the first production electric motor to use a carbon sleeve rotor, a thin layer of carbon fiber, wound around the rotor under high tension. The reason nobody had done it before is a materials problem. Carbon and copper expand at very different rates when they heat up. Get it wrong and the sleeve either loosens in the cold or cracks under load. Tesla had to build the winding machine itself, through its automation division, because no such machine existed. What the sleeve actually does is worth understanding, because it is usually described badly. It puts the copper rotor into compression. That compression stops the rotor expanding outward under radial acceleration, which is the force trying to tear a spinning rotor apart. With that expansion contained, the rotor can spin considerably faster before it becomes unsafe. The preload also helps hold a precise gap between rotor and stator, and a tighter, more consistent air gap means a stronger effective magnetic field. There is a thermal benefit too. Carbon fiber conducts less heat from the stator into the rotor, which lowers the risk of the magnets demagnetizing at high temperature. That matters, because heat is the quiet limit on every electric motor. Push a motor hard for long enough and the control system will reduce its output to protect it. A motor that stays cooler holds its full performance for longer. Now, a note of caution, because this technology gets oversold constantly. Motor design specialists have pushed back publicly on the framing of the carbon sleeve as revolutionary. Retaining sleeves are a known concept in high-speed motor engineering. What Tesla did was make one work in mass production, in a car, at automotive cost. That is a manufacturing achievement rather than a physics discovery, and the distinction matters when you are trying to judge how far ahead the company actually is. The third lever is everything around the motor. Tesla has said its next drive unit would use around 75% less silicon carbide in the power electronics, work with any battery chemistry, and require roughly half the factory footprint to build. So the answer to the question is that there is no single trick. Weaker magnets get compensated for by shape, by speed, and by the electronics around them, all at once. Which is exactly why this has taken longer than anyone expected, and why the thing Tesla shipped in 2026 is not the thing it announced in 2023. And what actually did ship is worth going through properly, because the headline number everyone quoted turns out to be the least interesting part of it. If you are getting something out of this, a like genuinely helps this channel reach people the algorithm otherwise skips. The 2026 Model Y Performance is the car carrying Tesla's newest motor hardware, and the numbers are real. Combined output 510 horsepower. The previous generation Model Y Performance made 456. That is a gain of roughly 50 horsepower from the same footprint. 0 to 60 in a claimed 3.3 seconds, which is about 3/10 quicker than the car it replaces. Quarter mile in around 11.5 seconds. System torque estimated at 513 pound-feet. Top speed electronically limited to 155 miles per hour. The rear drive unit is described as Tesla's fourth-generation design, shared with the refreshed Model 3 Performance. And here is the detail almost every write-up buried. The front motor is an induction motor. The rear motor is the permanent magnet synchronous one. That is not an accident, and it is not a leftover. Tesla runs a rare earth-free motor on the front axle of its performance cars already, and has for years. Induction motors are excellent at high power, and lose very little when they are not being used, which suits a front axle that spends most of its life idle, and occasionally has to deliver a lot. The permanent magnet motor sits at the back, doing the efficient everyday work. So the dual-motor Tesla in 2026 is a compromise made physical. The magnet-free technology the company is named after handles the burst. The magnet-dependent technology handles the range. The battery moved too. The pack is in the low 80s of kilowatt-hours, with published figures varying between roughly 81 and 84 depending on the source, using new cell chemistry with higher energy density in the same physical size. EPA range came out at 306 miles, which is more than 10% better than the previous performance, despite the extra power. Peak charging around 250 kilowatts, base price just under $60,000. More power, more range, lower price than the outgoing car. That is a genuinely good result. So the shock is real. It is just not the shock that was advertised. Nobody deleted a rare earth element. Tesla built a better version of the motor it already had and made it faster and more efficient without changing what the magnets are made of, which would be a fine place to end the story, except for what happened to the supply chain in between. In April 2025, China imposed export controls on 7 heavy rare earth elements and the magnets made from them. This was not a price move. It was a licensing regime, and the effect on the industry was immediate. Automakers in the United States and Europe trimmed production while licenses were worked through. Not because the magnets became expensive, because they became uncertain. Think about what that means at a factory level. A car is a few thousand parts and it needs all of them. A drive unit missing its magnets is not a slower car. It is a car that does not get built. An assembly line does not care whether a shortage is temporary. In October 2025, China went further, introducing a rule targeting any foreign-made product containing more than a trace amount of Chinese rare earth content, at a threshold of 0.1%. That reaches far beyond magnets. Almost anything with a motor, a speaker, or a sensor in it could fall inside that definition. And then, on November 7, 2025, China suspended that expansion for 1 year as part of a broader trade truce. That word suspended is doing enormous work, and it is the reason none of this slowed down. The controls are paused, they are not withdrawn. Every automaker on Earth now knows precisely how exposed it is, and knows the clock on that pause is finite. So the 2023 announcement stopped being an efficiency project and became something closer to insurance. Tesla was not chasing a marketing line about clean supply chains. It was trying to remove a single point of failure that a foreign government can switch on and off. Which brings us to the part that is genuinely hard to look at. 3 years after that Investor Day slide, there is still no confirmed commercial deployment of a rare earth-free Tesla drive unit, not in public filings, not in production disclosures, not in investor materials. No production date has ever been given. The motor exists as a design intention. It has not been shown to exist as a product. And the reason traces straight back to that 1/9 number. Ferrite is the obvious substitute, and it is proven technology. General Motors used a ferrite-driven permanent magnet motor in the second-generation Voltec powertrain in the 2016 Chevy Volt. The Japanese materials company Proterial, formerly Hitachi Metals, has shown ferrite-based EV motor designs more recently. One of those Proterial designs matched the output and the maximum rotational speed of a comparable neodymium motor. It did it while being about 30% heavier. Sit with that trade for a second. You remove the dependency on China, and you add roughly a third to the weight of the drive unit. In a car where every kilogram costs range, and range is the number on the window sticker that closes the sale, a 30% heavier motor is not a small compromise. It is the kind of compromise that loses a comparison test. That is the wall. The alternative works. The alternative costs you the thing you were competing on. And there is a second pressure that almost nobody accounted for in 2023. Humanoid robotics. Every joint in a humanoid robot needs a compact, high-torque actuator, and compact, high-torque actuators want the strongest magnets available. If robotics scales the way its backers expect, demand for rare earth magnets goes up, not down, at exactly the moment the industry is trying to design its way out of them. So the honest position after 3 years is this. Tesla identified the right problem earlier than almost anyone, said so publicly, moved a mining sector's share price by saying it, and then ran into the same physics wall as everybody else. Now the other side, because it would be easy to be unfair here, and the fair version is more interesting. Tesla did not achieve nothing. At the same investor day, the company said it had already reduced the rare earth content in the Model 3 powertrain by about 25% since 2017. That is a real, shipped, measured reduction, delivered quietly over 6 years without a headline. The front induction motor is a second piece of real progress that predates the announcement entirely. Every dual-motor Tesla is already running one axle with no rare earths in it. The carbon sleeve is real too, whatever you make of the language around it. Tesla built the machine that makes it. That capability does not transfer to a competitor just because the concept is understood. And the strategic read on the 2023 announcement was correct, which is easy to forget now. Tesla flagged rare earth dependency as a serious risk 2 years before China turned it into a live trade instrument. Most of the industry was still treating it as a footnote. There is also a fair argument that not shipping is the right call. A 30% heavier drive unit in a car sold on efficiency would be a bad product decision made for a good geopolitical reason. Holding the technology back until it is genuinely competitive is defensible engineering discipline, even though it looks like failure from outside. So the verdict is split, and it should be. The announcement was right. The timeline was fantasy. Both things are true at once, and any version of this story that only tells you one of them is selling you something. Tesla is not alone in this, and where the competition sits tells you how hard the problem really is. BYD builds its own motors, its own batteries, and its own semiconductors, and that vertical integration is its structural advantage. But building your own motor does not exempt you from where the magnet material comes from. BYD faces the same dependency, closer to the source. Toyota has spent years pursuing magnets that reduce or reallocate the heaviest rare earth content, rather than eliminating it. Hyundai has pushed in a different direction entirely, focusing on 800-volt architecture and charging speed, which improves the ownership experience without touching the magnet question at all. And there are smaller players taking swings. A Bengaluru startup called VMag Labs recently secured a 5th Indian patent for a motor that produces its magnetic field through software and power electronics, rather than fixed magnets. A $5 million company attacking a problem that has held up Tesla and General Motors for years. The odds are long. The fact that it is being attempted at all tells you how valuable the answer would be. Every serious automaker is now aiming at the same target from a different angle. More range per kilowatt hour, less dependency, cheaper to build. The company that gets there first does not just win a spec sheet comparison. It removes a lever another government currently holds over its production line. Here is why this matters even to someone who will never buy a Tesla. 3 practical things. 1. When a manufacturer announces a technology with no production date attached, treat the date as the news rather than the technology. Tesla's zero rare earth motor has been 3 years without one. That gap is the most informative part of the announcement. 2. If you are cross-shopping electric cars on efficiency, understand that motor design is now doing as much work as battery size. 2 cars with the same size pack can differ meaningfully in real-world range because of what is happening in the drive unit. Range figures are a motor story as much as a battery story. 3. Watch the supply chain news, because it reaches your driveway faster than you would expect. The April 2025 export controls trimmed production at real factories within weeks. Availability and lead times on specific trims move for reasons that have nothing to do with demand. And here is the rule underneath all of it. Every efficiency gain has a supplier attached, and the further you push efficiency, the more concentrated that supplier tends to be. The best material almost always comes from the fewest places. That is the trade the entire electric vehicle industry made without discussing it, and it is now the trade everyone is trying to unwind at once. So where do you land? Was Tesla's zero rare earth motor a genuine engineering goal that physics has simply not caught up with yet, or was it a promise the company already knew it could not keep on any useful timeline? Drop it in the comments. Everyone gets read. Which brings up the one Tesla where everything in this video matters more than anywhere else, the Cybercab. This whole video has been about squeezing more distance out of every unit of electricity. The Cybercab is that idea pushed to its limit. It runs a battery less than half the size of the one in the Model Y Performance, and Tesla is still targeting roughly 200 miles out of it. because a car that works all day only earns money if it spends almost none of that day charging. And there is something strange happening with how it charges. Tesla said the Cybercab would ship with no charge port at all, wireless induction only, park over a pad, no cable, no human. Then validation units started appearing with a conventional NACS port tucked behind a small drop-down door in the rear bumper. Meanwhile, the FCC has already granted Tesla the waiver for the radio technology the wireless system needs to line the car up. So one of those two things is no longer the plan. Which one it is tells you a great deal about how close the robotaxi actually is. That video goes through what the Cybercab really costs to run per mile, whether those numbers survive contact with reality, and what quietly changed between the reveal and the production line. If you want that one fast, say so in the comments. If enough of you ask, it goes to the front of the queue. See you in the next one.